Good evening, everyone, and welcome to August's Atom streaming event. Apologies again for the last-minute change of venue. I'm afraid it's back to just looking at my face this evening rather than me seeing all of you. I'm really excited, though, to hear from our speaker this evening, so we really didn't want to cancel, and I'm glad that you've been able to join us remotely this evening. We don't really have very much admin to crack on with this evening. Again, calls for anyone to join the committee if you want to get involved with the society. We have had one person come forward to help us with the tech, and that's really great. But if anyone else wants to get involved, we're always willing to take willing volunteers rather than trying to press gang you all into helping us out. And if you have any ideas for sort of speakers or any topics that you would like to hear speakers talk about, and we can try and hunt some speakers down for you, then please do get in touch via the usual methods. We are hoping that next month's talk will be back at the North Court, but we will communicate if there is a change. And to clarify, that is the North Court as in Abingdon Football Club, not the North Court Centre, as I think may have incorrectly been published in Random About. So before we get on with the main event this evening, then obviously we have our science snippets. I can see that a few of you have managed to join us on YouTube. So if you have any science snippets from the evening, from the month, then please do shout. And equally to our speaker, if you have any, then feel free to pop them in just before your talk. We will gladly welcome them. One that I have this evening, while you type your response furiously into the chat, is an article that was published this week in Science, was estimating the number of T-Rexes that roamed the Earth. And this isn't at any one time, this was in total. And so the estimate that these calculations came up with was that there were about 2.5 billion T-Rexes would have roamed the Earth at some point across a couple of million years. So it's quite a few. It's about 120,000 generations of T-Rexes, if you'd rather your numbers in generations rather than T-Rexes. So, yeah, I thought that was quite interesting. Frank is posing a question. So Frank would like to know, Frank, obviously our speaker from last month, Frank would like to know, can anyone give an opinion on Lawrence Livermore's claim to have made the biggest advance in fusion for 50 years. I'm afraid this is a little bit out of my wheelhouse, so I would not be able to comment on this, but if anyone else has a comment, then please do pop it in the chat. Obviously, Frank, if you have your own thoughts and feelings, then please do share them, and we'll see. Maybe it'll be an extra discussion on YouTube alongside the chat about the mathematics of knitting and crocheting. Okay, so Neale has a reply, Frank. Just wait for it to pop up on my, there we go. Neale says, yes, they want more money. With a cynical view there, perhaps, but as I said, not my area. Okay. Frank's follow-up question, if so, what is the qualitative advance? And his question is genuine ignorance based on a story in the Times. Okay. And Neale, Frank agrees with you. So, okay, so I feel like I've just facilitated a little conversation between the two of you now. But if anyone else wants to get involved, then please do. In the meantime, I think we can swiftly move on to our main event this evening. So, as I said, I'm really excited to welcome our speaker this evening. We're being joined by Dr. Vicky Neale, who is the Whitehead Lecturer at the Mathematical Institute at the University of College and a Supernumerary Fellow at Balliol College. Sorry, University of Oxford and Supernumerary Fellow at Balliol College. As well as being an accomplished mathematician and lecturer, part of her role is also to discuss mathematics with a broader audience. And to that end has been involved in television and radio shows for almost 10 years now, has various podcasts, videos that she's been involved in, as well as various charitable events, getting children involved in mathematics and excited about science and mathematics, which is something that I am very keen on. And if you want to know more about all of those fabulous things, she does have a personal page. She's also published 2 books, which are available at all good retailers. This evening, she will be talking to us about, as I said, crocheting and knitting and math. So scarves, some symmetry and solving equations, and how through her knitting, she's been exploring the symmetry patterns in scarves, and how many different types of scarf patterns there are, and what does this have to do with finding a formula to solve certain types of polynomial equation. So with that said, I'd like to bring Vicky in. Thank you for joining us, Vicky. Welcome. And your slides are on the screen now, and away you go.
Great. Thank you so much, Danielle. Thank you for the introduction. And it's a great pleasure to be joining everybody. I'm sorry it can't be in person this evening, but thank you for inviting me to join the Atom Society this evening. I want to talk to you about my knitting project, and maybe you can see in the background a recent crochet project that I worked on. The design is by a crochet designer called Janie Crow. I adapted the colours a little bit and made it. So I want to talk to you a little bit about that, and I do want to talk about solving equations. One of the reasons that I thought I would share this with you is one of the things that I like most about maths, which is those unexpected connections, maybe when you think you're dealing with this bit of maths or you think you're dealing with that bit of maths, and then it turns out that actually they sort of behind the scenes, they link up, that there is some underlying structure that they have in common, that really what you're seeing are different examples of the same phenomenon. And for me, that's one of my favorite things about maths. I like it when I'm studying a particular topic in maths. I like it when I'm working on a problem and I sort of know it squarely sits in this area. But my absolute favorite problems are the ones where ideas come in from all sorts of different places. And this is, if you like, one concrete illustration of that. I hope to be able to share a little bit of that with you this evening. Some bits are a little bit more technical, some bits are a little bit less technical. So I will try to do my best to make it not too intimidating for this evening. So yeah, here are some scarves. I've got some slightly bigger photos on my slide. If I show you some pictures. So here are 3 scarves. And just to confirm that these are real life scarves, but they curl up terribly. I had to do lots of elaborate pinning to take the photos, and they really don't work massively well on camera. So this is why I took photos. But in case you doubt whether these are genuine scarves, they are genuine scarves. I have a whole pile of scarves on my kitchen table at the moment. And I'm interested in these scarves because they might have some symmetry, or they might not have symmetry. And as a mathematician, I respond to symmetry, but actually I don't think this is anything to do with being a mathematician. I think that as people, we respond to symmetry. We instinctively, as I'm talking, I imagine you're looking at these scarves and instinctively, maybe not even consciously, noticing types of symmetry that the scarves do or don't have. I sort of feel like that's just what we do when we're kind of responding to pattern. One of the things is responding to symmetry. And so it seems to me quite natural to wonder what different types of symmetry a scarf could have, a knitted scarf like this, how many different, genuinely different scarves there are. So 2 scarves count as the same if they have the same kind of symmetries here. So how many different types of scarf are there? Those kind of things. So just to kind of set out the ground rules a little bit, there are a few rules, not very many rules, but some rules. One rule is that these scarves are infinitely long. Breaking news, the ones on my kitchen table are not infinitely long, but for the purposes of mathematics, these scarves are infinitely long. And each of them is made up of a repeating block, sort of a strip across the width of the scarf that then repeats endlessly in either direction. So my scarves are not beautifully square in these photos, but I hope you can kind of see, I've tried to highlight a repeating block on the red scarf there, and on the yellow scarf, and on the blue scarf. So each of them has a single repeated block all the way along its infinitely long length. And small technical detail is that they have to have this kind of discrete repeating block. So for my purposes, a plain green scarf wouldn't count, because a plain green scarf you could think of as having one of these repeating blocks of kind of any width you like, and that sort of violates the rules. So it's just the kind of scarves that I've got on the screen here, where there is these kind of discrete repeating block of some smallest possible size, and then it repeats infinitely in both directions. And for me, that counts as a type of symmetry. So I would call that a translational symmetry. So I guess that's not the kind of symmetry with a mirror that I learnt about when I was little at school, but it's a mathematical kind of symmetry in the sense of you can do something to the scarf, and at the end of it, you can't tell you've done anything. So reflection type symmetry, you can reflect, and at the end of it, you can't tell you've done anything. This translational symmetry, you could imagine moving this infinitely long scarf sideways by the appropriate amount, and at the end of it, the viewer wouldn't be able to tell that you've done anything. So that's the kind of symmetry that I have in mind here. So all of the scarves I'm interested in are infinitely long, and they all have this kind of discrete translational symmetry. But then you can already see with these three scarves that there are other types of symmetry that they might or might not have. And that's where it gets maybe a little bit more interesting. So the red scarf at the top has, I'm going to call this a kind of lengthways line of symmetry. So a line of symmetry across the middle lengthways along the scarf. And if you reflect in that line, you can't tell anything's happened. Quick check, do either of these other two scarves have that? No. The yellow scarf, if I flip, the sort of undulations don't quite match up. You'd flip a short, so a low undulation and a high undulation. They would kind of exchange places, but you'd be able to see something different had happened. And the blue one, these diamonds are sort of much more intricate at the bottom. So there's no lengthways line of symmetry there. So that's one type of symmetry that the scarf might have or might not have. There might be a kind of widthways line of symmetry, and these would be vertical if I'd managed to get my scarves slightly straighter when I was photographing them, but the knitting was fighting back. But actually you can see that each of these three scarves has one of these widthways lines of symmetry across the width of the scarf. And again, if you reflect, you can't tell that you've done anything. So you have to position the line in the right place. It matters where it is in the pattern, in the repeating block, but these three all do. Does every scarf have this kind of line of symmetry? Well, that's a question that this slide does not resolve. These three all do have this kind of widthways symmetry. Are there other kinds of symmetry? There are. A scarf could have rotational symmetry. So this is my sort of slightly suspect computer graphics attempt to illustrate. If you put a pin in the right place in a scarf and rotate the scarf by 180 degrees, so kind of flip the ends, except there are no ends because it's infinite, can you tell you've made a difference? And the red scarf and the yellow scarf, if you position your pin carefully and then rotate by 180 degrees, you can't tell you've done anything. The blue one, you would be able to tell, kind of roughly speaking, because the complicated diamonds and the simple diamonds would have swapped places. So a scarf might have rotational symmetry 180 degrees, or it might not. I guess it's not going to have rotational symmetry by another angle, because if we rotated by an angle other than 180 degrees or a multiple of 180 degrees, then the whole scarf would be in a kind of different orientation, and we'd be able to see immediately that we'd done something. So we had translational symmetry, all of them have, that's the rule. They might have lengthways reflection symmetry, they might have widthways reflection symmetry, they might have rotational symmetry. I feel like that's kind of the sorts of symmetry that I learned about at school. It turns out there is another one, and I think maybe I just wasn't concentrating when we learned about that at school or something. This other one is called a glide reflection, and it's a sort of combination of a lengthwise reflection and a translation. So if I look at the yellow scarf in the middle, if I reflect that in a line that goes lengthways along the scarf, as I said before, we can tell we've done something. That is not a line of symmetry. But if we do that reflection and then slide the scarf along by an appropriate amount, we can't tell that we've done anything. So that glide symmetry fixes the yellow scarf. We can't tell that we've done anything. In the case of the red scarf, because it's got a lengthways line of symmetry already, that's sort of also a glide reflection. You could just reflect and not glide at all. Or if you like, you could reflect and glide by one pattern block or something. The blue scarf still does not have this kind of symmetry, again, because the complicated diamonds and the simple diamonds would somehow swap places. So the top two scarves here have this glide reflection type of symmetry as well. And you have to stop and think a little bit to convince yourself of this, but it turns out that those are the different types of symmetry that a scarf might have. So they have to have translation symmetry, that's my rule. They might have lengthways reflection, they might have widthways reflection, they might have rotation by 180 degrees, and they might have a glide reflection. And once you know that, you think, well, okay, so how many types of scarf pattern are there? There are various types of symmetry that a scarf might or might not have, but it's not clear that those are totally independent, because maybe if you have one type of symmetry, you're forced to have another one as well. In fact, we saw that red scarf, because it had a lengthways reflection symmetry, it automatically was going to have a glide reflection. And maybe there are other combinations that if you have this one and this one, then you must also have this other one. So it's not completely clear how many there should be. It's sort of, I think it seems plausible that there are already finitely many types of scarf pattern in the world now with these rules. But it's not quite clear what that number should be. That's something that kind of you have to stop and think about a little bit. And I promise I will answer this question this evening, but I'm not going to answer it right now. So if you want, you can kind of have a little think about it. And in fact, if you like doodling and you want to doodle during the rest of this talk, that's all good with me. I've got some designs on a slide I'll show you in a second on just coloured pens on square paper. You could think about what symmetries those do or don't have. There are two quite interesting different directions here. So one thing is come up with a design and then analyse what symmetries it has. A little bit like I was just showing you those scarves, and then we were asking, well, what symmetries do they have or not have? A sort of slightly harder but very mathematical version of this problem, I think, is pick some combination of symmetries and ask, can you come up with a design with those symmetries? Which is in fact exactly what I had to do for this scarf project. I sort of sat down with my paper and thought, okay, what are the possible types of symmetries that I can have? Can I now design a pattern, not only a pattern, but a pattern that I can knit that will have that particular combination of symmetries? And I did a lot of drafting and redrafting at the paper stage just to make sure I got the symmetries right. Also at the knitting stage when I decided some of them looked horrible. So yeah, if you want some inspiration for your doodling, I just printed some square paper off the internet, got my felt tip pens out, did some colouring in. So if you would like to doodle for the rest of this evening, I shan't be offended at all, and you can have a nice time thinking about your symmetries. So just imagine you've got an infinitely long strip with some discrete repeating pattern. Let me talk about something apparently slightly different, but as we'll see, maybe not so different, which is about the symmetries of a square. Here's a square I prepared earlier. It's not a massive square. Look, oh, sorry, it blew away. Let me hold it slightly closer to the camera for you. So there's my square. And what I'm interested in is what are the symmetries of a square? And the problem with this is that if I have an unlabeled square and I just kind of turn it or something, I can't tell that I've done anything, which is the point of a symmetry, but also I can't tell that I've done anything, which makes it quite hard to keep track. So I've just numbered the vertices here, just so that we can tell when we've done something. So what kind of symmetries can my square have? Well, as I was just sort of hinting at, we can rotate. So that is one type of symmetry that a square might have. We can also reflect, and I can reflect, for example, in an axis that goes through the midpoints of two opposite sides, so this sort of vertical axis. Officially, what I'm doing with my piece of paper is rotating in 3 dimensions because I can't reflect a 2-dimensional square on camera, but we can reflect a 2-dimensional square in the idealized mathematical world, just not so much on my piece of paper. And So we can reflect and we can rotate. We're not going to be able to do anything involving translation because the square would then move. Remember, the deal is that somehow we have to do this to the square and it has to end up exactly in that kind of position that it's already in. So I can rotate by multiples of 90 degrees. I can reflect in other axes as well. So the one I've got on the slide is reflecting in a vertical axis, but of course I could reflect in a horizontal axis. I could also reflect in a diagonal axis. The reason that I haven't drawn that on my slide is that we can achieve those further reflections by doing some combination of reflect in a vertical axis and rotate by an appropriate amount. So we can actually achieve, it turns out, you have to stop and think about this a little bit, but it turns out you can actually achieve all of the possible symmetries of a square by some appropriate combination of rotating, now I'm going to get in a pickle with my camera, whichever way, rotating anti-clockwise, so I guess this way, rotating anti-clockwise by 90 degrees, which of course I could do repeatedly, or reflecting in a vertical axis. And I've just drawn here the effects of these two transformations. So the effect of the reflection in the bottom left, and then the effect of the 90-degree anti-clockwise rotation in the bottom right. And I have slightly mysteriously drawn a blue line between the original and its reflection, and a red arrow between the original and the rotation. The reason I haven't drawn arrowheads on the blue one is that it's reversible, that the arrow actually goes both ways. If you start with the diagram on the left and reflect it, you end up with the one on the right. But if you start with the one on the right and reflect it, you end up with the one on the left. That is not true of the red arrow. If you start with the original square and rotate 90 degrees anti-clockwise, you end up with the diagram on the right. If you start with the diagram on the right and rotate 90 degrees anti-clockwise, of course, you don't end up with the original position. But then you can chase round and say, well, what happens if I do a blue arrow and then a red arrow and then a red arrow? Or, what are the different combinations? And when you do that, you end up with a diagram that potentially looks something like this. I mean, there are variations depending on exactly how you arrange things. So what I'm seeing here is kind of two nested squares, one inside, one outside. And if you look at the inner one, in the top left-hand corner is the square with the numbers in their normal configuration. And then going around the inner square following those red arrows corresponds to rotating repeatedly 90 degrees anti-clockwise. Reflecting in the vertical axis from any of those takes you to the outside corresponding square. And it turns out that following those red arrows around in the opposite direction, it all sort of stacks up. So I could start with my original square, and if I want to know what's the effect of doing blue, red, red, I can chase that around in the diagram. I can start in that original square, move out following the blue arrow, move down following the red, move to the right following the red, and see where I end up. So this diagram kind of captures all of the possible symmetries of the square. These are all of the possible configurations, and for each position, you can see where we get to by doing a blue arrow or a red arrow. And it's quite interesting to think about why the arrows on the outside go the opposite way from the arrows on the inner square. That's sort of to do with whether you're looking at the front or the back of the piece of paper in some kind of interesting way. So this is a diagram that kind of captures everything that we might want to know about the symmetries of a square. Not really clear what this has to do with scarves, but let's not worry about that. Let's just talk about symmetries of a square for a little bit. And if I don't want to keep drawing pictures of my square with the numbered vertices, I could just replace each by a dot and actually simplify the whole diagram. And one advantage of simplifying the whole diagram like this, and replacing each of these numbered squares by a black dot, is that we could then imagine that this diagram could describe other situations with the same combination of symmetries as a square with numbered vertices. So we know this diagram describes the symmetries of a square, but in principle, there might be other objects whose symmetries could be described captured by this diagram. And we would see, because they have the same diagram, we would see that they somehow have the same structure, that we could analyze the diagram mathematically and know that whatever conclusions we draw would apply to the square, but also to this other kind of object. So I rather like this diagram kind of way of capturing what's going on. And it's not just squares. We could do this with an equilateral triangle as well. And when you stop and think about it for a little bit, there are two types of symmetry that an equilateral triangle can have. You can reflect in an axis through a vertex, a corner, and the midpoint of an opposite side. So there's a reflection, and there will be three of those, but actually you can achieve all of those by doing a reflection together with some appropriate rotation about the center of the triangle. And I always have this overwhelming instinct to think this is rotation by 60 degrees, but it really isn't. It's rotation by 120 degrees. And if you do that 3 times, you end up back where you started. And in a similar kind of way, you could number the vertices of a triangle, track what happens under each of these two symmetries, and then try to construct a diagram of all of the possible symmetries of an equilateral triangle. And I think rather beautifully, it has very much the same kind of structure as the symmetries of a square. It's just more triangular. But again, there's this kind of inner shape with red arrows going one direction, and that same shape on the outside with the arrows going in the other direction. And to pass between the inner and the outer, we can use the reflection. And again, there might be other objects. There are other objects with this same kind of configuration of symmetries. So what I'm showing you here, these are called Cayley diagrams to describe some groups. So what is a group? There is a technical definition, and I don't feel like this evening is the time for a technical definition of a group. Consult Wikipedia or find a book on group theory if you want a technical definition. But roughly speaking, a group is a set with an operation that satisfies some axioms. Really, it's the kind of structure that we've just seen, like the symmetries of a square, like the symmetries of a triangle, like the symmetries of a scarf, in fact. So the group of symmetries of a regular square is called a dihedral group. I would call that D8. Some people will call it D4, and then D6, or some people call it D3 for an equilateral triangle, and so on. And it turns out you can play this game with a polygon with any number of sides. So a regular polygon with n sides, a regular n-gon, has associated with it a group, one of these mathematical structures that we can describe visually using a Cayley diagram. And you might boldly, wildly extrapolate from Cayley diagram for a triangle, Cayley diagram for a square, to know what the Cayley diagram for a regular n-gon would look like. And you would be right. That is not a mystery. This is a really geometric interpretation of symmetry, which seems like a natural place to look for symmetry because that's how we tend to use the word symmetry. I think when we use the word symmetry in everyday life, we're talking about that sort of visual type of symmetry. But there are other types of symmetry as well, and I want to try to touch on that a little bit. So let me move on to something apparently different, and maybe it will turn out to be not quite so different after all. Let's talk about solving polynomial equations for a bit. This is going to get slightly more technical, hopefully not off-puttingly so. If you want to tune out and keep doodling diagrams of scarves, I will wake you up again when I get to revisiting scarves in a few minutes. Let's think about solving polynomial equations, because this is something that we learn about at school. We learn this thing called the quadratic formula. So we have a quadratic equation like ax squared plus bx plus c equals 0. And it's quadratic because the highest power of x there is an x squared. And the quadratic formula tells us how to solve this equation, that the solutions are minus b plus or minus the square root of b squared minus 4ac all over 2a. And the details of the quadratic formula are not important right now. What is important is that there is a formula, and that the ingredients in this formula are the coefficients from the equation, the numbers in front of the x's are the powers of x, so a, b, c. We're allowed to feed those into the formula, and we're allowed to use addition, subtraction, multiplication, division, and taking roots. And with some appropriate combination of addition, subtraction, multiplication, division, taking roots, and the coefficients, we can write down this formula that tells us the solutions of this equation. And maybe we have to think carefully if the number under the square root is negative, but it's okay because really we should do this in the complex numbers. I'll tell you about the complex numbers in a moment. The key point is we can solve quadratic equations. There is no mystery whatsoever about quadratic equations. If you have a quadratic equation, there's a nice formula to solve it. Nice meaning it just involves these kind of familiar operations of addition, subtraction, multiplication, division, and we're allowed to take roots. What they don't tell us at school, at least they didn't tell me at my school, was what happens if you have a cubic equation. So that would be something like ax cubed plus bx squared plus cx plus d equals 0. So similar kind of shape, but with an extra term because you're allowed a power of x cubed. Somehow we don't learn about the cubic formula at school, but there is a cubic formula. I think the main reason we don't learn about it at school is that it's not very illuminating and it's quite complicated and it's not massively helpful. But there is a cubic formula. In general, if you take a cubic equation, you can write down a formula in terms of its coefficients using addition, subtraction, multiplication, division, and taking roots. You can write down a formula for what the roots of that equation will be, what the solutions are. And this was the subject of kind of contentious history. So if you go back in the history of algebra, people fell out over this because they were sort of closely guarded secrets for solving cubics. I think sort of 16th century, because they were nervous about negative numbers and so on. It's sure quite an elaborate process with the benefit of modern notation and modern understanding of how numbers work and so on. It's a little bit more streamlined. But yeah, this was something that 16th century mathematicians spent their time wondering: how can we solve cubic equations? And the answer is, well, there is a formula. So they say, well, what about quartic equations where the highest power of x is x to the 4? And they definitely don't teach us about that at school. But it turns out there is a quartic formula. It's not very nice. It's not massively illuminating. You sort of might try to simplify your quartic to make it look more like other things. And it's all kind of complicated. It's quite interesting. But we don't need to solve quartic equations that often. So we don't learn the formula in the way that we learn the quadratic formula or whatever. And it feels like this game could just keep going. Maybe mathematicians through the decades, through the centuries, get better and better at solving polynomial equations and figuring out some ferociously complicated formula to be able to solve a polynomial equation of whatever degree, whatever highest power of x you like. But the thing is, that's not how it is at all. Because actually this game stops right here. There is not a quintic formula. By which I mean, it is possible to write down a quintic equation, so a polynomial of degree 5, so the highest power would be something x to the 5 plus something x to the 4 and so on, equals 0. You can write down a polynomial of that type where you cannot find an expression for the roots just using addition, subtraction, multiplication, division, and taking roots. There is not, in general, a quintic formula. So there is a formula that will solve every quartic equation. As with the quadratic, there is a formula that will solve every quadratic equation. There just isn't a formula that will solve every quintic. And in fact, at that point, it's sort of game over. So it doesn't work for powers higher than 5 either. I mean, how mysterious is that? It seems really strange that something works for degree 2 and degree 3 and degree 4 and then breaks with degree 5. Like, why should that be different from degree 4? It's really quite mysterious. A mathematician spent quite a long time thinking about this, and the sort of early pioneers were able to show that there isn't in general a quintic formula, but that theory has subsequently been refined in all sorts of ways and is now really kind of key part of the machinery of modern pure mathematics. I guess it's been refined and honed and streamlined and made more complicated to tackle more sophisticated problems and so on. And I'm just going to try to give you a tiny flavour of that this evening. This is quite ambitious. We normally teach this to our third-year undergraduates who've got 2 years of undergraduate maths knowledge. I'm completely sure that some of you know all of this kind of stuff already, but I also suspect that some of you don't. So I just want to try to give you a little bit of a flavour, and also a little bit of a flavour of what on earth this has to do with my knitted scarves and with the symmetries of a square. So Let's think about complex numbers briefly. And I'm sure that some of you have spent lots of time thinking about complex numbers. So this is a sort of whistle-stop tour for people for whom they're new. Complex numbers sound scary, particularly because they're called complex. I think this was really bad kind of marketing on the behalf of complex numbers. They should have been called something that didn't make them sound difficult. So a complex number is of the form a plus b times I, where a and b are just ordinary real numbers, and I is the square root of -1. If you haven't come across complex numbers before, then my blithely saying the square root of -1 might feel like an alarming moment, because there is no ordinary real number that when you square it gives -1. Because if you square any number, you always get an answer that's greater than or equal to 0. So this is a fundamentally new type of object. But my advice is just not to have an existential crisis about this. Just kind of roll with it. Okay, so I is this thing. We're not quite sure what it is, but let's not worry. All we need to know is that I squared equals -1. That's what it means to be square root of -1. If you square it, you get -1. So one way of thinking about this is that the real numbers lie on the number line, the real line. The complex numbers are kind of two-dimensional. They sort of fill a plane. You could have sort of coordinates a comma b for the complex number a plus bi. And the complex numbers I'm interested in this evening are ones where a and b are both rational numbers, which just means a fraction. So I'm interested in this thing called q adjoin I, which is all the numbers of the form fraction plus fraction times I. So here are some examples. 7/2, that is a complex number. 7/2 is a complex number. We don't have to have an I part. We can just have a 7/2. 1 plus I, that's a nice complex number. -5i, so we don't have to have the a bit. We can have a being 0, just have -5i. 19/7 -3/5i, that was just a random complex number I wrote down. I don't know anything particularly interesting about this complex number. There are other complex numbers where the coefficients aren't necessarily fractions, but I'm not interested in those this evening. So that's why I haven't got any examples on my slide. I'm only interested in complex numbers of the form fraction rational plus rational times I. And what I'm really interested in is, what are the symmetries of q adjoin I? And I've introduced q adjoin I in this quite algebraic way. It's just a description of what numbers look like. And it's not quite clear then, what does it even mean to talk about a symmetry of q adjoin I? I know how to think about symmetries of a square, because symmetry is a sort of geometrical property, and it's a square and it can have this geometrical property or not, or whatever. But what about q adjoin I? So this is a slightly different type of symmetry, but for me as a mathematician, it fits that same bill of a thing I can do to the object, and at the end of it, I sort of can't tell I've done anything. So the deal with the square was I could rotate anti-clockwise by 90 degrees, and at the end of it, you couldn't tell that I'd done anything, except I helpfully numbered the vertices so you could. With my scarf, a symmetry might be that I could rotate by 180 degrees, which I can't really do on camera, and at the end of it, you can't tell that I've done anything. So it's kind of, what can I do to q adjoin I so that at the end of it, we can't tell the difference? That's sort of what we're looking for here. And the idea can be kind of captured by the idea that we can swap I and -I, and q, which stands for the set of rational numbers, the set of fractions, q can't tell the difference. So somehow we can swap I and -I, and the rational numbers won't notice. Let me try to tell you what I mean by that, because that's a sort of slogan. So in a little bit more detail, if I give you an example, here is an equation involving complex numbers, which is true. So 2 plus I all squared minus 4 times 2 plus I plus 5 is equal to 0. You don't have to check it's true. You can trust me. This is a true equation involving complex numbers. What I'm going to do is swap I and -I. So now my equation becomes 2 minus I all squared minus 4 times 2 minus I plus 5 is equal to 0. And it's still true. I've swapped I and -I. All of the numbers in this equation are rational numbers. They're fractions. In fact, they're all whole numbers here. This is still a true equation. I've swapped I and -I, and we can't tell the difference. So if we have these kind of polynomial expressions involving complex numbers, if we swap I and minus I, we still have a true equation. We can't tell that we've done anything. So formally, you can write down a map. You can say, okay, take A plus BI and send it to A minus BI. This is sort of formally describing the symmetry, if you like. And that has two key properties. It fixes all of the rational numbers. It doesn't move them around. So f applied to 7/2 will be 7/2 and so on. And any polynomial equation with rational coefficients is unchanged, as in that example I just showed you. So this counts as a symmetry of Q adjoin I. It's a thing that we can do to Q adjoin I, and we kind of can't tell we've done anything. Are there any other symmetries of Q adjoin I? Well, we can't just do whatever we like. So if I try to define a map where I send A plus BI to A plus 5BI, for example, that wouldn't work because, for example, we've got an equation I squared plus 1 equals 0. That's a true equation because I is the square root of minus 1, so I squared is equal to minus 1. But if I have 5i, it's not the case that 5i all squared plus 1 is equal to 0. So it's not a free-for-all. I can't just do whatever I like. I can't just rotate my square by whatever angle I like. There are kind of rules. There are kind of rules here. So we can swap I and minus I. Is there anything else we can do? Well, sort of extrapolating from this example, you see we have to send I either to I or to minus I because we have to send it to a root of the equation x squared plus 1 equals 0. There is another possibility, which is the keep everything still map. And actually, that is an important symmetry of the square too. We don't normally talk about it because it's quite boring, the do nothing map, the identity map. But it's a perfectly good symmetry of the square. It's also a perfectly good symmetry of my scarf. The do nothing symmetry is also a symmetry. That's true for Q adjoin I as well. You can just leave everything alone. And it turns out those are the only two possibilities. When you kind of explore the fine details of what it means to be a symmetry, those are the only two possibilities. And actually, they form a kind of group structure. It's not a very exciting group. So my diagram here only has two vertices, but it does have a group structure. There's the identity and there's the map F that was swapping I and minus I. And we can sort of think of having a map between those. And if you do the swapping twice, you end up back where you started. So it's again a reversible blue arrow with no arrowheads on it. So the symmetries of Q adjoin I also form a group, and we can draw a Cayley diagram of them, although it's not a very exciting Cayley diagram. If you look at more complicated scenarios, you can come up with more complicated groups of symmetries. So fairly briefly, we could think about, instead of having Q adjoin I, we could think about Q adjoin the square root of 2 and the square root of 3. So this time there are no complex numbers. So an element of this setting is called a field, would be something in the form A plus B times the square root of 2 plus C times the square root of 3 plus D times the square root of 6. And then you can ask, what are the symmetries? And you can sort of extrapolate from the kind of thinking with Q adjoin I. Well, where can I send root 2? Where can I send root 3? The options are constrained a little bit in the same way that they were constrained a little bit with I. So there are a few possibilities. There's the identity, there's the do nothing symmetry. That is always a winner. We could swap root 2 and minus root 2, but fix root 3, and you can write down a formula for what that does. Or analogously, we could swap root 2 and we could swap root 3 and minus root 3, but leave root 2 fixed. And again, you can write down a formula for that. And I've called those maps F and G. If you do F then G, or in fact G then F is the same thing, that will have the effect of swapping root 2 and minus root 2, and also swap root 3 and minus root 3. So you can sort of swap everything that can possibly be swapped. You can't swap root 2 with root 3 because that would violate some kind of polynomial equation, a bit like we couldn't swap I with 5i earlier on. So this time it turns out there are 4 symmetries. I mean, I've sort of whistled through that. You have to think about it a little bit, but it turns out there are 4 symmetries. And again, they form a group. And again, we can draw a Cayley diagram. So I've got the identity in F and G, and then GF or FG, whichever the sort of result of doing one, then the other. F and G are both swapping. So again, they're reversible. And I've used different colors for them because they're kind of different things in the same way that I had blue and red, different colors for the rotation and reflection with the symmetries of the square earlier on. So these settings, we can assign groups. And these settings, these things are called fields, the Q adjoin something, you kind of cook up from a polynomial. So if you have a polynomial, you could then throw in the roots of that polynomial. So in the case of Q adjoin I, you can think of that as what happens if you take the rational numbers and throw in the roots of x squared plus 1 equals 0. You can do something similar but slightly more complicated to construct Q adjoin root 2 and root 3. Think of that as being built from the roots of a polynomial. And all of this belongs to a branch of mathematics called Galois theory. Galois was not the first person to think about the solvability of the quintic. Is there a quintic formula? He was building on work that other people did, but he kind of had some really innovative new ideas. He also has this very dramatic life story because his life was rather short and ended in a duel in 19th century, 18th century. Now I've got my dates muddled. Anyway, he died in a duel in France. Not a mathematical duel, some combination of political and personal life, I think. So yes, the story of Évariste Galois is a dramatic one, and it's worth going and looking up a biography if you are intrigued. So what is Galois theory about? Well, roughly speaking, you take your polynomial equation, you cook up one of these field extension things, you take the rational numbers and throw in the roots of your polynomial. It's slightly more subtle than that. You have to be a bit careful, but that's kind of the idea. And from that, you get a group of symmetries. In the sort of way that we've just seen, you can construct a Cayley diagram, you can construct a group of symmetries associated to a polynomial equation. And then you can understand the structure of that group. You can forget all about your polynomial now. All that matters is, if you like, the Cayley diagram, the group structure. You can forget where you got it from. It doesn't matter. Maybe it turns out that it's got the structure of the group of symmetries of a square or of an equilateral triangle or of some other kind of group structure. You now have all the power of group theory. And since the time of Galois theory, there is a lot of group theory. So you have all the power of that to understand the structure of this group. You can really explore that in quite an abstract way. And it turns out that the structure of that group is enough to tell you whether or not you can solve this polynomial. We say in radicals. That means addition, subtraction, multiplication, division, and roots. The radicals bit is the roots. So you sort of take away the polynomials in a way and just study the groups, which is kind of extraordinary. And this is sort of what we mean by algebra in the university maths context. So at school, I learned about algebra as replacing numbers with letters, and then you could work with letters and know that it would be true. Your manipulations would be true, whatever numbers you substituted in. This is sort of like that, but another level up. You look at the group structure, you prove things about the group, and then know that it will be true wherever that group appears, whether it's symmetries of a scarf or symmetries of a square or symmetries of Q adjoin I. And the final detail is that there is a quintic, a polynomial equation of degree 5, whose Galois group is not solvable, that you can't solve it in radicals. So that is the kind of punchline to this Galois theory story that shows that there is no quintic formula. There is a quartic formula and there is no quintic formula. And when you study Galois theory, you sort of discover why there's a difference between degree 4 and degree 5. I mean, it's kind of mysterious. Why on earth should degree 5 be different from degree 4? It doesn't feel like it should. And it turns out to be to do with the associated groups and what's going on in a really intriguing way. There is a kind of reason. It still feels to me ever so slightly mysterious. It's still sort of slightly surprising. It sort of doesn't feel inevitable that the dividing line should be between 4 and 5. I can see that it is, but I wouldn't have been any more or less surprised if you told me the dividing line was between 3 and 4, or the dividing line was between 6 and 7. Other successes of Galois theory. It turns out that you can use Galois theory to study some really classical problems that the ancient Greeks like to explore. So ancient Greeks like to ask themselves what they could construct using compasses and straight edge. So compasses as in drawing circle compasses, and straight edge as in a ruler but with no markings on it. So literally just a straight edge. You can't measure a calibrated amount. You can use your compasses for measuring a bit, but you can't use your ruler for it. So there are lots of things that you can do with compasses and straight edge, but there are also some things that it seems like you can't, and the ancient Greeks spent a long time worrying about this. And Galois theory, it turns out, gives a beautiful way to resolve some of these classical problems, and there are three really famous ones. So one is about constructing regular polygons. So with compasses and straight edge, you can draw a perfect square or a perfect equilateral triangle, but you can't draw some polygons with some numbers of sides. And Galois theory can be used to make sense of which ones you can draw and which ones you can't. Trisecting the angle. So if you have an angle, you want to find half of the angle, you want to bisect it, you can do that with compasses and straight edge. In general, you can't trisect an angle to split it into three equal parts. Some angles you can trisect, but some you can't, and you can show that with Galois theory. And then the other problem is called doubling the cube. So the ancient Greeks are very interested in this. If you have a cube of a certain volume, the goal is to construct a cube whose volume is twice as big. So essentially the side length, if your side length of your original cube were 1, you'd need to construct a cube with side length the cube root of 2. It's just not possible. And these problems worry people because it sort of feels like, well, maybe mathematicians are just saying, well, we tried very hard to trisect the angle and we haven't thought of a way yet. And sort of people think, well, if only I tried hard enough, maybe I could. But it's really genuinely impossible. You can prove that, for example, with Galois theory. So when people say, oh, it's not possible to prove a negative, I get really annoyed because we do this all the time in maths. It's absolutely possible to prove a negative. It is possible to prove that it is impossible to, for example, trisect every angle. And Galois theory is your friend. So Galois theory builds on the idea of groups and symmetries. Those are absolutely pivotal to Galois theory. And Galois theory is now, as I said, one of the key bits of modern machinery, being used in all sorts of bits of pure mathematics, also being used in other kind of contexts, I think. But I'm a pure mathematician, so that's my interest. Let me go back to scarves, because we have a loose end hanging here, which is very messy when you're knitting. So I've got some scarves, and the question is, how many are there? And it turns out that you can't have every possible combination of symmetries. There are some where if you have these two, then you have the third one as well, and so on. So it's quite fun to sit and play with that. It turns out that there are 7 types of scarf pattern. And so naturally, I decided to make a rainbow of them. So I have a red scarf, and the red one has every possible type of symmetry going, basically. And then this isn't quite in a straight line because some of them have the same number of symmetry, just different combinations. But I do have a full rainbow of scarves illustrating each of the 7 different types of scarf patterns. So if you've been drawing scarf patterns or drawing just patterns with color pens on square paper or whatever, perhaps you've come up with patterns for some of these 7. Some of these I find it easier to think of than others in terms of trying to work out what I could do in the way of knitting. I really like the purple one. The purple one has no symmetries apart from translational. So the rule is it has to have translational symmetry, but I worked very hard to make sure that it doesn't have any of the others. I kind of did that by putting together 2 motifs. So there's the sort of lattice work type motif, and then there's the plait along the edge, and each of those kind of breaks some other symmetries. So that is the worst behaved, or possibly the most interesting, depending on your perspective. The red is the best behaved or the most boring, depending on your perspective. And then the others in between have various combinations. I quite like these twists. Twists are quite good because they give you rotational symmetry, but not reflectional symmetry, that kind of thing. And these are symmetries of scarves, but the same mathematical structure applies in other contexts as well. So here is close-ups of these scarves. These are called frieze groups in mathematics. There are 7 frieze groups. Frieze in the architectural narrow band with repeating pattern sense. So I guess if my hobby were carving stone, then I would have carved 7 frieze patterns, but I like knitting, so I knitted 7 scarves instead. I also made friendship bracelet versions of them. I mean, not versions of the scarves, but 7 friendship bracelets illustrating the different symmetry patterns that are possible, because I wanted to share them with other people. And if you don't know how to knit, learning how to knit is a bit of an investment. Friendship bracelets, it's quite easy to learn how to make a friendship bracelet. So I had a lot of fun designing those, and the design process is quite different because I was using color, because what you can do in a friendship bracelet is quite different design wise from what you can do in knitting, or at least what I can do in knitting. So I had a lot of fun playing with those. My favorite friendship bracelet is definitely this one, which is the bottom left on the slide, because it looks to me like a sort of folded piece of ribbon, which it isn't. It's just a flat friendship bracelet. I cannot tell you how long I spent drawing with my felt tip pens on graph paper to come up with a design for that friendship bracelet. I knew it must be there somewhere. One of the things I found quite interesting about coming up with these friendship bracelet designs was that I had to come up with a notation to be able to design a friendship bracelet on a piece of graph paper. And that meant kind of understanding the friendship bracelet technique well enough to find a notation to be able to capture that. And in itself, that felt to me like a really mathematical thing to do. That kind of, how can I capture exactly what's going on, was, and I kind of like my designs as much as I like the friendship bracelets, if I'm honest. I was quite pleased with those. So yes, there are these 7 frieze groups. There is a related idea called wallpaper groups. So frieze groups is kind of linear patterns, but you can also ask what happens if I'm covering a piece of wallpaper in a repeating pattern, or indeed, as in the blanket behind me, covering with repeated crochet shapes. So this blanket is made up of octagons and squares, which nicely tessellate in a repeating manner. You can ask about the group structures, how many different types of wallpaper pattern there are. That's a really interesting piece of mathematics, but not for this evening, I think. I had to go at drawing some Cayley diagrams of the groups associated with some of these scarves. So this isn't a complete set, but this is some of them. And one of the things I like about this is that it's sort of quite self-referential, in that you take a scarf with some symmetry patterns, you find its group and draw its Cayley diagram. And I've got 3 Cayley diagrams here. But then each of those Cayley diagrams is kind of another scarf pattern in a way, or sort of frieze pattern with repeating things. So then you can ask, what's the Cayley diagram of the Cayley diagram? And that's a really fun game to play, but also I think I shouldn't play that game this evening. Let me just wrap up by acknowledgement. So the Cayley diagram idea, this is an idea that's explored and important in mathematical research. I found the book Visual Group Theory by Nathan Carter really helpful for organizing my thinking on that. If you are interested in looking at some Galois theory without getting an undergraduate textbook, there's a nice free article on the Enrich website, which I recommend. You have to concentrate. It's quite sophisticated mathematics, but it's aimed to be approachable to maybe sort of 17, 18-year-olds who've done school maths but haven't started doing university maths. And if anyone is interested in looking at the scarves or the friendship bracelets, or indeed you want knitting patterns for scarves, they're all on my webpage. And on that note, I think I will stop and see whether anybody is still here with us, or whether I'm talking to my laptop and nobody else. Thank you very much for listening, if you are still here.
Thank you very much, Vicky. I definitely am still here. You lost me a little bit sometimes with the tech. I came in and out with the technical.
That's very understandable.
Yeah, no, it was really good, really good, really enjoyed it. I did also do some doodling with my pattern.
Oh, that's very intriguing.
Yeah,
nice.
I was trying to get a few. I didn't quite get all the forms of symmetry that I was trying to get, but
I think you've got some nice glide reflections going on.
Yeah, there. That was one of the things I wanted to get.
Yeah, nice.
So that might also be why I slipped in and out with the technical. Cool. So if anyone has any questions, I'm just going to bring up the app so I can see if anyone's typing. Yes, if anyone has any questions, please pop them in the chat for Vicky, and I can bring them up as well. Susan, I can see that you have connected with the committee. So if you have any questions, please wave at me, and I'll bring you in. So yeah, I I have many questions, but they're possibly far too basic.
There is no such thing as too basic.
For me, yeah, I got to AS level maths, and I think if someone had sat there with more visual aids, the scarves and things, it would have been much better. Is the way that you communicate maths? I find it quite intriguing. Is there more of a move among the newer generations of academics to try and communicate mathematical ideas like this to the wider populace in a more accessible way? It always felt very stuffy and dry when I was younger. Is it more of a move, or are you a bit of a maverick?
I don't think I'm that much of a maverick. I may be unusual in deciding to spend quite as many hours as I did designing and knitting scarves. That is possibly excessive when you could just draw a picture. But also now I've got this mound of coloured scarves, so I'm never going to be cold in the winter. I think lots of people are exploring visualizations, and I think for me it's really interesting to see how different students, when I'm working with my undergraduates, respond to different ways of looking at ideas. And actually, when I was a student, I wasn't a particularly visual person. I'd somebody would say, draw a diagram of this, Vicky, and I draw some sort of microscopic kind of mechanics diagram in the very top corner of my page, very grudgingly. And my teacher would say, for goodness sake, Vicky, draw a proper diagram. And I did eventually learn that drawing a proper diagram is actually a good idea. My teacher was absolutely spot on. So I feel like I don't necessarily instinctively reach for the visual. I'm often quite comfortable with the algebra. That's not true of all of my colleagues, whom I have plenty of colleagues for whom it's the other way around. But I feel like I have a richer understanding when I can also access those visualizations and when I can relate those. I think often it's not just having a way of looking at it, but having multiple ways and seeing how they link up. I feel like that's when I kind of, okay, I think I properly understand this. And I think we are, increasingly trying to share those. And I think visualizations can be very powerful for people who haven't had lots of mathematical training, as kind of giving a way in to see what's going on. If I stopped spending my time knitting and learn how to use my computer properly, I probably be doing clever animations. And there are some fantastic maths communicators out there doing really innovative things with kind of video and animation and that sort of visualizations that are much more sophisticated than was actually possible some number of decades ago. And I think it's that variety, I think, is really powerful. And I think that human instinct to respond to color, pattern, aesthetic, movement can be really enticing. And then you kind of, okay, I'm curious about that. Now there's a reason why I want to try to make sense of this idea in whichever way.
Yeah, I think that's really insightful. I'm a biologist, broadly. And yeah, this is why I moved away from maths and physics when I was younger, was because I find it much easier to understand things when they're tactile. And I couldn't hold all the ideas in my head. And I think having someone going, yeah, but look at this scarf, and then look at this scarf, and what does it mean? For me, that would have been much.
And even better when it's you creating your own piece rather than, it's one thing looking at my scarves and go, okay, so Vicky made some scarves, but if you're able to have a go at creating your own diagrams, I think sometimes we're not very broad-minded about what mathematical thinking looks like. And as I said, the process of, okay, I've learned the technique for making a friendship bracelet. I know what to do with the yarn, but how do I capture that in a diagram? How do I notate that so that I can explore the structure and so that I can look at a diagram and know what the bracelet will look like and will it have the right symmetry and so on? That feels to me like absolutely as mathematical thinking as, what's the quadratic formula about? They're just different facets of it. So I think people are increasingly aware of that, and hopefully persuading people to put that into kind of school curriculum and give lots of young people those kind of opportunities.
I had a similar experience when trying to design a quilt pattern, patchwork pattern. But yeah,
it's very much the same kind of thing, definitely.
So Frank has posted a question. So 7 is an interesting number, and this is the first time I've seen it enter maths fundamentally. Can you say why there's 7 scarf symmetries or name them? If it needs a PhD in topology, then perhaps.
Well, I'm very honoured to find Frank in the audience today, having come across his books. So thank you, Frank. It doesn't need a PhD in topology. And actually, if you look up frieze groups on Wikipedia, for example, you'll find there's sort of notation that gets used to describe these. There isn't really a snappy name for each of the 7. But the mathematician John Conway spent quite a lot of time thinking about frieze groups and also the wallpaper groups. I'm waving vaguely at this blanket behind me to the sort of wallpaper groups. And he's got this sort of nice way of looking at it, thinking about, you can think about kind of what patterns of letters of the alphabet or footsteps, footprints, and those kind of things. So there's really less scarf-based ways of describing these. I don't think I know deep down really why 7 rather than 6 or 8. I can sort of work through it. There are some nice arguments. There's something called Conway's magic theorem that sort of sheds a bit of light on this. So I'm not sure that I'm going to supply which 3 these are off the top of my head this evening, but there are 3 of these symmetries that I mentioned that if you have 2, then you have the 3rd as well. So that cuts down the possibilities automatically, because you can't have these 2 without that one. So that possibility is already ruled out. And there are a few that you cross off the list for those reasons. And that's essentially the kind of idea that, well, if you've got this one, I must have that one as well, or whatever. So yeah, Conway's magic theorem gives a kind of intriguing way of thinking about these, and also about the wallpaper groups. But yeah, it doesn't need a PhD in topology, definitely.
Thank you very much. Just a comment to say fascinating stuff, and I love the Oxford comma in your title.
Thank you. It was a carefully chosen Oxford comma, so I'm glad it was appreciated.
So Andy has asked, how would you sell algebra to secondary school students who struggle to see the applicability of it to everyday life?
I think that's an interesting question, and I'm not sure I'm necessarily the best place to answer it. I often get asked what's the point of the maths that I'm interested in, and often the answer is just, I think it's really interesting. I mean, I spend lots of time thinking about prime numbers, about groups, symmetries, and all of these kind of things. And honestly, I'm interested because I think they're beautiful and intriguing, and I'm curious, and I want to make sense of these ideas. That's not a very compelling reason for somebody who is finding it hard to see the beauty or feel curious about it or whatever. I absolutely get that. But I'm also a little bit wary of spurious reasons for being interested. Well, I'm interested in this thing because it's tangentially related to this other thing. I sort of feel like people see through those kind of claims pretty quickly. So I would rather just be upfront and honest, because I would love secondary school students to have the opportunity to experience the beauty of maths, the playfulness, the patterns, the curiosity. Not that I think they're all going to choose to do a maths degree. I don't actually want them all to choose to do a maths degree, because as a society, we need people to do lots of things, but so that they have an opportunity to experience that, because I genuinely believe that everybody can experience those things at whatever level of mathematical experience they have. That's not exclusive to those of us who've got a PhD in maths or whatever. So actually, I would just really like students to have that opportunity. I go and work. What am I saying? It's a pandemic. I don't go anywhere. I used to go and work with groups of teenagers. So I work with groups of teenagers in my kitchen these days. And inevitably, sometimes I get students saying, sort of halfway through we're doing something, oh, hang on, what's the point of this? And I think often what they're saying is, I'm a bit confused. I don't quite understand what I'm supposed to be doing. I'm feeling a bit lost. I don't think it's really... I mean, I don't doubt their sincerity. I'm sure they're interested in what is the application of this, but I think that's often a cry of, I'm lost, I'm confused, I don't get it. Why am I supposed to be interested? And I sort of feel like at that point, it's my job to kind of try to address those issues rather than invent some spurious application. Of course, maths has loads and loads of applications, and I'm super happy that it does, and I find them fascinating too. But that's not what I'm about, I guess. So when I'm having those conversations with teenagers, I sort of try to address that, but then also, what's the issue with the maths here? Can I help with that? Can we get back on track by addressing whatever it is that I've confused you with, or that I've not been clear about, or those kind of things? that power of abstract thinking, the power of algebra to say, instead of doing this calculation and this calculation and this calculation and this calculation, I'm going to do one calculation once, and then it will answer all of those. I think that's fantastic. And I think that thinking is relevant in lots of contexts too. I think we can sort of appreciate that structural kind of thinking. Oh, okay, I could write a computer program. Instead of doing this job and this job and this job, I can write a computer program that will do all of these jobs all at once. You know, that kind of algebraic thinking, I think, is really powerful. And I would love more secondary school students to feel confident with that, even if the finer mechanics of the quadratic formula or whatever may be kind of challenging.
Yeah, thank you. I really like that answer. I think, yeah, I in my interactions with kind of secondary school students, I try to enthusiastically geek out about the things that the reason I do the things I do is because I'm really geeky about them, and someone has decided to pay me to keep doing them, right? So I think showing young people that it's okay to be excited about something is also a powerful thing. So that's
definitely, yeah.
Cool, thank you. So Frank also said thank you, and that Conway's magic theorem sounds interesting. So I'm sure.
Yeah, I recommend it.
And have a look. Cool. So I think that's the end of our questions for this evening. Thank you so much again for joining us for the talk. I really enjoyed it, and it looks like so did our audience. And
thank you for inviting me.
And everyone else, as I said, hopefully we will be back in person next month, but obviously check your email inboxes to see any updates on that. Thank you very much. Bye.